Welcome to AI Paper Podcasts. Today we are breaking down a really exciting one, RLAnything, Forge environment, policy, and reward model in a completely dynamic RL system. This is from researchers at Princeton University and Genverse.
Yeah, this paper is a big deal. It really tackles one of the fundamental problems in training agentic LLMs.
Which is that whole sparse reward problem, right? These really long, complex tasks.
Exactly. So think about controlling a computer or writing code. An agent makes dozens of moves, and it usually only finds out if it succeeded or failed at the very, very end.
So RLAnything creates this closed loop. It's not just training the agent, the policy. It's also training the reward model. And it is the key part. It's dynamically changing the tasks in the environment based on how the agent is doing.
Right. It uses something they call critic feedback. If your agent fails, the system literally rewrites the task to make it a little easier, maybe adds a hint.
And if it's succeeding too easily, it makes it harder.
It makes it harder, exactly, to keep the learning curve optimal. And the results are, well, pretty staggering. We're seeing a 9.1% boost on OSWorld for GUI agents and a huge 18.7% jump on AlfWorld.
Okay, that's the 1-minute summary. Now let's really get into the weeds because the architecture here is just so clever.
It really is.
So to set the stage, let's talk about why this is even necessary. We've all seen these amazing reasoning models, like DeepSeek R1 or the O1 style models that use RL, but they're mostly for single-turn chain of thought stuff.
Right.
Why can't we just use that same pipeline for these big agentic tasks?
Well, it all boils down to the density of the reward signal. In a math problem, the verification is pretty straightforward. You got the answer right or you didn't. It's immediate.
But in an agentic world, like controlling a computer in OSWorld,
you're dealing with what we call long horizon tasks. You have to open a file, click a menu, type something, save it.
a whole sequence of actions.
Exactly. Let's say it takes 50 discrete actions. In a standard RL setup, if step 49 is wrong and causes the whole thing to fail, the agent just gets a single fail signal.
Which tells it nothing. It gives the policy zero gradient to learn which of the 50 steps was the problem.
It's the credit assignment problem on steroids. I mean, that's what it is. And the usual fix is to train a reward model, basically an AI judge, to give step-by-step feedback.
But that's super expensive, right? You need humans to annotate thousands of trajectories to train that judge.
That's the bottleneck. It's not scalable. And then there's the other problem, the one people don't talk about as much, the environment itself. The tasks are usually static.
Right, you download a benchmark data set and the problems are fixed.
And that's a huge issue. If the tasks are all too hard, your agent just fails 100% of the time.
So it never sees a success.
And your reward model only ever sees bad examples. It just collapses and learns to predict fail for everything. But if the tasks are too easy, the agent just, plateaus. It stops learning.
So RLAnything is this triple threat. It's fixing the policy signal, the reward model's training data, and the environment's difficulty all at once. Let's start with the first piece, the policy. They mention integration feedback in equation 1. What's going on there?
Okay, so normally you're just optimizing for that final reward. Did you win or lose? Let's call it OTAU.
The outcome.
The outcome. Here, the policy gets a composite signal. It gets that final outcome, OTAU, but it also gets the average of all the stepwise signals from the reward model.
So it's a much denser signal.
It's so much denser. Even if the final task is a failure, a 0, if the reward model thought the first 10 steps were logical, the policy still gets a little bit of a positive gradient for that part. It just smooths everything out.
But yes, and this feels like a big but. That totally depends on the reward model being any good. If the reward model is just guessing, aren't you just adding noise?
And that is the perfect lead-in to component 2, optimizing the reward model itself. This is where they use what's called consistency feedback. It's a way for the reward model to learn without any human labels at all.
Okay, how does that work? How do you get ground truth without a person?
You use the final outcome as your anchor. So let's say the reward model is watching a trajectory and it predicts step 5 is great, a really high-value move.
It's confident.
Very confident. But then the trajectory plays out and the final verifiable outcome is a failure.
So there's a mismatch, an inconsistency.
Exactly. That inconsistency creates a loss signal for the reward model. It's forced to go back and say, my stepwise prediction didn't align with objective reality, so it updates its own weights.
It's like it's doing hindsight experience replay on its own judgments. The reward model learns from the policy's mistakes.
Precisely. But again, for that to work, you need a mix of successes and failures. If the agent fails every single time,
the reward model just learns that every step is bad. It can't tell a good step from a slightly less bad step.
And that brings us to what I think is the most sci-fi part of this paper. Component 3, the dynamic environment, the critic feedback.
This is the system rewriting its own homework.
It is. So the agent fails a task. The reward model doesn't just say fail, it identifies the specific step where it went wrong.
Let's use that OSWorld example from the paper, the spreadsheet one. I thought that was brilliant.
The agent had to calculate employees' ages from their birth years. It fails. The reward model analysis pinpoints the exact error. The agent clicked AutoSum instead of the function wizard, the little FX button.
A very specific, understandable mistake.
Right. So the system takes that summary, used AutoSum instead of function wizard, and feeds it to another LLM that acts as a task editor.
And it rewrites the prompt.
It rewrites the prompt. The new task becomes calculate the age. And by the way, make sure you use the function wizard, not AutoSum.
It's injecting a hint directly into the task description.
It is. And the result was incredible. The agent's success rate on that specific task went from 0 to 25%.
It broke the cold start problem. The agent finally got a positive reward, which gives the policy a good signal, and it gives the reward model a positive example to learn from.
And then, of course, once the agent gets too good,
The environment adapts the other way.
it makes the task harder. If your accuracy goes above a certain threshold, it ups the difficulty.
This is the soap bottle example.
Yeah, from the text-based game AlfWorld. The task was to find a cloth. The agent was doing great. It would just check a drawer and find it. Too easy.
Right.
So the system saw this high success rate and swapped the target. It changed cloth to soap bottle.
And why a soap bottle?
Because in the games world, soap bottles are just rarer. They're harder to find. This immediately dropped the agent's accuracy from about 87% down to 50%.
Which forces it to learn a better strategy.
It forces the policy to learn a more robust search algorithm. It can't just check the first drawer anymore. It has to learn to check multiple containers, navigate different rooms. It's automated curriculum learning.
And that's what's so cool. Normally, a human engineer has to sit there and design level 1, level 2, level 3. Here, the system is diagnosing its own specific weakness and then patching the environment to teach itself.
And this isn't just a cool hack. This ties directly into the theory in the paper theorems 1 and 2. They basically prove mathematically that for the reward model to learn effectively, you need a balanced data set. You need a mix of good and bad examples.
So making the environment dynamic isn't just a feature, it's a mathematical necessity to stop the reward model from collapsing.
That's it. It keeps the agent in what you might call the zone of proximal development, constantly challenged, but not overwhelmed.
Okay, let's talk numbers. The results. They ran this on OSWorld, AlfWorld, and coding benchmarks.
The OSWorld results are probably the headliner here. I mean, controlling a real Ubuntu desktop is messy and hard. They took a Qwen 3 VL model and improved its performance by 9.1%. That's a big deal.
And importantly, it wasn't just on tasks that it had seen before. They tested on out-of-distribution tasks.
Right, tasks that were completely new that hadn't been rewritten for it, and it still showed a 5.2% improvement. That proves it's not just memorizing the hints, it's learning a generalized policy for controlling a computer.
Okay, I want to pull in one thread here from figure 6 in the paper. This, to me, was one of the most surprising findings. They compared training with the verifiable outcome, the perfect ground truth signal, versus training only with the AI's stepwise rewards.
This is so counterintuitive. We always assume that ground truth is the gold standard.
Of course. Did the code pass the unit test? Yes or no? That's objective.
But they found that the signals from the learned reward model, the AI's own judgment, actually produced better final performance than training on the sparse ground truth signal alone.
So a dense, slightly noisy signal is more valuable for learning than a sparse, perfect one.
It seems so. The AI judge is providing feedback at every single step, guiding the agent. The final outcome signal is just yelling at you after you've already driven off the cliff. It implies we might be able to build better agents by relying more on these learned reward models, not less.
That's a massive unlock for scaling this stuff. If the reward model can bootstrap itself effectively, you don't need to write a perfect verifier for every task in the universe. And speaking of not needing a visual world, let's talk about the coding domain. How does this apply when there's no GUI to click on?
Well, in that setup, the environment is basically the test suite, and the reward model becomes a unit test generator.
So the agent is writing code, and at the same time, the system is writing tests for that code.
Yes, it's almost an adversarial process. The reward model's job is to generate a good unit test. And a good test is one that passes the correct solution, but fails an incorrect one.
So if it just writes a lazy assert true test, it gets a bad reward because that test would pass buggy code.
Precisely. The system optimizes for tests that can actually discriminate, and the environment adaptation happens here too. If a coding task is too easy, say a 100% pass rate,
The system makes it harder.
it injects a constraint. The example in the paper was a simple task. Append a character to a string. Way too easy. The system rewrote it to append a character, but make sure that character is not already in the original string.
It added an edge case,
Yeah.
a negative constraint.
It did. And that forced the model to learn to handle that case. On LiveBench, this whole approach took the pass rate from around 31% up to over 43%.
That's a huge leap in coding ability. It really shows how this whole dynamic loop policy reward model environment works together.
It just fundamentally changes how we think about data sets. A data set is no longer this static file you download. It's a living, breathing thing that adapts to your model's current skill level.
It's a fully closed loop. The policy creates data for the reward model finds errors for the environment, and the environment designs new problems for the policy.
And because it's a closed loop, you can just scale it with compute. You don't need a human to come in and write new prompts or label more data. You just let the simulation run.
Before we wrap, I want to leave our listeners with one final thought. We often hear about curriculum learning, where humans carefully design tasks from easy to hard. RLAnything kind of flips that on its head. It suggests that the AI can construct its own curriculum, perfectly tailored to its own failure modes. If an AI can inspect its own mistakes and then literally rewrite the world to teach itself the exact concept it's missing, are we looking at the blueprint for a kind of autonomous self-improvement?
That's the provocative question, isn't it? It's a shift from learning from static data to learning from dynamic, self-generated interaction. It's a much more powerful paradigm.
A really profound paper, again, that was RLAnything, Forge Environment, Policy, and Reward Model in a completely dynamic RL system. If you're building agents, you have to read this one.
Absolutely essential reading.
That's all for this edition of AI Paper Podcast. Thanks for tuning in, and we'll see you for the next one.